Okay, so we're continuing on with this, and we're looking at this idea of velocity, and the area under the velocity function is a displacement. So the question is giving me the velocity function, and I want to know the displacement from t equals 2 to, we want to know the displacement at t equals 2. And you're given the initial condition that at time equals 0, the distance is 1, or the displacement is 1. Okay, so I want to integrate this. I want to find the area underneath that curve. However, when I try to integrate this function, I don't have an antiderivative for this. Okay, so what do? Well, I have to look for some alternate methods. Okay, and the one that I have right now is our substitution method. So I'm going to let the inside function, u be the t squared function. Okay, because that's really the only thing that's embedded inside that function. So u equals t squared. I'm going to then differentiate this, and I get du is equal to 2t dt. Okay, well, that is great because although I don't have a 2t dt, if I rearrange this, I can go du over 2, and the constants really aren't an issue. I can move those constants anywhere I want, and I get t dt. Well, there's the outside portion that I need to accommodate. So I can replace the t dt with a du over 2. So that's what I'm going to do. So I'm going to rewrite this integral. Okay, so this is going to be the integral of, I'm going to replace the t squared with a u. Okay, so there's my u function, and I'm going to replace the outside t dt with a du over 2. So then I'm just going to clean this up a little bit. Okay, so I end up with the integral of e to the u. I'm going to take the 1/2 outside du. Well, that's a very easy integral to do. I'm going to end up with e to the u plus c. Okay, so there's my displacement function as a function of, well, this is as a function of u. Okay, so I don't want this in terms of u, I want this in terms of t. So with 1/2 e to the u plus c. So I want it in terms of t, so I'm going to replace the u with a t. So my original u was t squared plus c. So then I can figure out, I need to know the displacement at t equals 2. To do that, I need to solve for c first. Well, to do that, I'm going to look at the initial condition here, and I'm going to plug that into my equation. And the only thing that's left to solve for is c then. So my distance, or my displacement, when time is 0, okay, so it's going to be 0 squared plus c, and that's going to be equal to my y value. Okay, so when d is 0, I plug in 0, and it should be equal to 1. So working that out, this is going to be equal to 1/2. 1/2 plus c equals 1. Well, I get, solving that equation, I get c equals 1/2. Okay, so my displacement function then looks like this. d of t is equal to 1/2 e to the t squared plus 1/2. Just going to move it over so that it's not all crowded in there. There's my displacement function. Okay, solve for my displacement function. Now I need to solve for when t equals 2. So d of 2 then works out to be 1/2 e to the power 4 plus 1/2. Okay, so there's my displacement at time equals 2. This tan function, well, I don't know how to anti-differentiate tan, and there's only really one piece in here. So how do I go about doing this? Well, the trick with tan is that we want to express this tan as sine over cos. And again, we don't really know how to anti-differentiate this. However, if we take a look at this function, well, there is an embedded cosine whose derivative will account for the outside sine. Okay, so that's what I'm going to look for. That's what I'm looking for. I'm looking for that embedded cosine, and I'm going to see if that works. So I'm going to let u equal cosine x. Well, then the du then, the derivative of that is negative sine x, and move the dx to that side. Well, there it is. There's the accounting for the outside function. Okay, so that I can now do a substitution here. And let's see what I have. So when I apply my substitution, I'm going to have the integral of 1 over cos, or u. Okay, so I'm going to write that as u. And then I'm going to replace the sine x dx. So I don't want a negative in there, so I'm going to put the negative on the other side. And I'm going to replace that with negative du. Okay, so that sine x dx gets replaced with a negative du. So there it is. I have my function in terms of u. I can now integrate this in terms of u. Okay, so this becomes negative log absolute value of u plus c. I can replace, back substitute for u, and there it is. There's my antiderivative function. Okay, it's going to be log cos u. So we should again check this. So I'm going to check. My check is I'm going to differentiate negative log cosine x plus c. The derivative of log is 1 over x, so I get 1 over cos, times the derivative of cos is negative sine. Okay, the negatives cancel out, so I end up with sine x over cos x, which is our tan x. There we go. We've proven that it works, right, using the fundamental theorem of calculus.